find some differentials. Very similar to finding the derivatives, it's just we include the differential of dy, dx, dv, whatever, to each piece that we take the derivative of. So when I take the derivative of y, I get 1. The differential is going to be 1 dy. The derivative of 14v to the 5th is 70v to the 4th. The differential is going to be 70v to the 4th dv. So, of course, we just clean this up as dy is equal to 70v to the 4th dv. The beauty of the differential comes when we have a function that's written in terms of multiple variables. In this case, when we have y equals e to the x secant of t, we recognize that these two things are being multiplied together, so we're going to have to use the product rule to get through this. The differential of y, like we saw before, is dy. Now, as we try to handle e to the x times secant of t, we have to use our product rule, which is 1d2 plus 2d1. The 1 is the first factor, e to the x. d2 is the differential of secant of t. The differential of secant is going to be secant times tangent of t dt. So that's our 1d2 plus 2 secant of t times d1, e to the x dx. So now I can see that that's where I took that derivative or differential, and I did it again right here. Our 1 d2 plus 2 d1. If we wanted to clean this up a little bit, we can take out some common factors. Each term has an e to the x in it, so I can factor out that e to the x. I also see a secant of t in there in both terms. But then that's it. After the e to the x and the secant of t are taken out of the first term, I'm left with the tangent of t dt. And in the second term, when I take out a secant and e to the x, all I'm left with is dx. It looks like this will be a quotient rule problem. So if I'm going to find the differential of y, we're going to do low d high minus high d low over the square of what's below. So the low is the denominator, z squared, d high, so 2 dw. Low d high minus high, the 2w, d low, which is 2z dz, over the square of what's below. And the square of z squared is z to the 4th. If we want to clean this up a little bit, I'd probably break it into a couple different fractions. The first one would be 2z squared over z to the 4th, and that's our dw. The next term would be 4wz over z to the 4th, and that's my dz term. Then I look for factors to cancel. I got 2 of them to factor out of here, and 1 of them to cancel with 1 of them in the denominator. So that will leave me with dy is equal to 2 over z squared dw minus 4w over z to the 3rd dz. Alright, this last one's got a bunch of terms in it, but I see some square roots and some stuff in the denominator. So before I get started, I'm just going to rewrite the function as m is equal to x to the 1/2 plus 4x to the negative 1 minus cosine of x. Alright, then I can use some power rules and stuff to help me through this. When I find the differential of m is going to be dm. Right. X to the 1/2, the derivative would be 1/2 x to the negative 1/2 dx, makes it the differential. For the next term, we have minus 4 x to the negative 2. That's also dx. And for negative cosine, the derivative of cosine is negative sine, so minus a negative makes it plus sine of x. And again, a dx. Cleaning it up maybe just a little bit, I do notice that every single term has a dx in it, so I'm going to factor that all the way out in front. And in my first term, I could rewrite that as 1 over 2 square root of x. In the second term, I got minus 4 over x squared. And my last term is plus sine of x. And like I said, all of them have a dx in it. I mean, you can go real crazy with trying to simplify that or rewrite it as maybe a single fraction, getting radicals out of the denominator, all sorts of things. But, I mean, that looks awfully pretty to me.